Hi, I'm Igor. I'm a data science living in London, and in this video I'll explain to you what a chi-square distribution is. This distribution is used a lot in data science, particularly for A/B testing, so it's something definitely well worth knowing about. In this video, things we'll cover are what is a chi-square distribution, some example plots, deriving it from first principles, and how it relates to the gamma distribution. So let's get into it. Let's begin with basically describing what the chi-square distribution is. So the chi-square distribution is quite simple, and all it is the result of summing up v random independent variables from the standard normal distribution, where we're squaring the variables. So in this case, x is from the standard normal distribution, and all we're doing is summing up different values sampled from that standard normal distribution, squaring them, and that is going to be the result of the chi-square. So in this case, v is the degrees of freedom, or the values number we're going to sample. X is a random variable from the standard normal distribution, which looks like this. So it has a mean of 0 and a variance of 1. And as you see here, a lot of the data points are concentrated around -1 and 1 standard deviation. And you see you're very, very unlikely to sample values at the extremes, right? So basically, we're very likely to get values between 0 and 1, plus or minus 1, and very unlikely to get any values outside that range. And like I said, the chi-square, all it does is it samples a value from the standard normal distribution, squares it, and that is it. Or it may, depending on what the number of degrees of freedom are, it may sample several of those values, square them and sum them up. And it really is all to it, and that's when the square comes in, right? The square is all about squaring these standard normal distribution values. So here's an example plot for where we have one sample. As you can see here, like in this case, we're sampling just one value, squaring it from the standard normal distribution. And as you see here, it's very kind of, well, yeah, it's leftly skewed, or like it's very, like the peak is to the left, which makes sense, right? Because if you go back to this, we're very likely to sample a value between -1 and 1. And when you square a value between -1 and 1, they actually get smaller. And so that's why we see the distribution kind of shift or be very skewed to this left-hand side, and we're very unlikely to get anything to the right-hand side. Again, it's the PDF, we're telling you the density. So you see you're very likely to get, the density is all centered around this left side part of the plot and very likely to be on the right because, squaring them, they're going to decrease in value. Now, if we do for free values, we see that it kind of shifts a bit more to the right, which is two reasons that's happening. The first one is that simply because we're sampling more values, we're more likely to get a larger value. We're more likely to get a value at these extreme cases the more we sample, by just pure probability. And because of this, it shifts to the right. And we're also summing values up, right? We're summing up one value, two value, three value from sample from the distribution. And because we're doing this, what that is saying is that, it's a summation, and we know it must be positive, so therefore the values can only get increasingly larger. They can't get smaller. And that's the reason why we have v equals 3. And you can see after a while that the more we sample, the more it's going to shift to the right. And that's just the nature of the chi-square distribution. But it really depends on the number of degrees of freedom you have. It's very kind of parameterized by. So I hope that makes sense. Again, it's very simple. It's just squaring values from the normal distribution and summing them up. And that is a chi-square. So it's parameterized by that v, which is one parameter. And now we'll show you what other values parameterized by deriving first principles. So, like I said, we can start deriving the chi-square distribution by first going from the normal distribution. So let's say we have a chi-square distribution and we have 1 degree of freedom. The normal distribution for that looks like this, right? This is a standard normal distribution with a mean of 0 and a variance of 1. And this is what it looks like in PDF form. So this is the PDF for it, the probability density function. Now, the way we calculate a PDF for most or pretty much any statistical distribution is by getting a CDF, because it's a lot easier to express, and we simply differentiate that function to get the PDF. So it's a well-known result of statistics that the derivative of the CDF is the PDF. And we can do this, but we can then kind of inverse it and then take the value we want to calculate as being the chi-square. We know it's a squared value. So if you look here on the screen, what we're doing is we're saying we're going to do d by dx, and we know the chi-square is a squared value of the normal distribution. So in this case, if x is our random variable from a normal distribution, we then know that our value for the chi-square needs to be a square root of that. And so when we do our derivative of this probability function, we know it's going to be bounded between minus root x and root x, right? Because, you know, x squared square rooted of x, it has two outcomes, you know, plus or minus root x. And that's what we do. And then we take the derivative of x, which is the normal distribution variable, and that will give us our PDF for the normal distribution. See, I hope that makes sense. It's kind of like a neat trick we're doing here, where we're using normal distribution to extract the chi-square distribution. So it's a very subtle, but it's very clever how this is done. Now, I've gone a bit cheeky here because, to be honest, this derivative here is a bit messy. Well, not messy, it's just tedious, and I don't want this to become like a really in-depth math lecture. There's textbooks on how you do this, so there's no point in me just reiterating that key point. This is all about building intuition and really understanding where it comes from and what it means. So I've omitted the full derivative here. I have linked this whole presentation in the description below, and in our presentation I've attached links here and here that you can look in if you want to know the full derivative from the CDF to the PDF. And by full derivative, what I mean is basically this formula here. But anyway, if you do that differential, what you'll find is that you get this formula, which can be rewritten in this format. Now, the reason we rewrite it is because we want to show how it belongs to the gamma family. So the PDF for v degrees of freedom, remember this was only for 1 degree, right? This is for v equals 1. We can generalize it for, you know, various degrees of freedom, so v, so loads of values of chi, loads of samples for the chi-square distribution, and this is written like this. We have x to the v as opposed to x to 1, which I have written here. And what we can do is this denominator is actually given by this gamma value. So gamma is this, and I kind of covered gamma in my previous video when I did the gamma distribution, and well, the gamma value is that's why the gamma distribution is called the gamma value. And in this case, we have the gamma value for half positive integers, which is slightly different. And this is written like this. This is what it's expressed at. Again, I wouldn't worry so much about this. This is just me explaining kind of the key concepts and like where the gamma distribution links into the chi-square. You don't need to know this. The main thing is that you just got to know where the chi-square comes from, the key points behind it, and you know how we use it, and that's just in using it for A/B testing. But it's really important to know the background behind it. So we can link that chi-square value to the gamma distribution. The gamma distribution looks like this. Again, I've done a previous video on it, but it's parameterized with two things: lambda, which is the rate of events, which comes from a Poisson distribution. Again, done a video on that, so make sure you check that out. Not spend too much time on it here. And n, which number of events we expect it to happen. So lambda is the kind of the mean rate of events, how many we expect, n is the value of what we're waiting for. And so this is what it looks like. Again, we have this gamma value at the denominator, which is why it's called a gamma distribution. And this looks very, very similar to the chi-square one we saw in the previous video. So by setting n equals v over 2 and lambda equals a half, in this case, we show here that a chi-square distribution is just a special case of the gamma distribution. Now, if you watch other videos in my series, you know that from the Bernoulli, you can get to the binomial. From the binomial, you get to the Poisson. Poisson, you can then get to the exponential. From exponential, you can then get to the gamma. And from the gamma, you can now get to the chi-square. But not only that, from a normal distribution, you can get to the chi-square distribution. So that means from the normal distribution, you can get to the Bernoulli distribution. And when you think about that image in your head, the normal distribution and the Bernoulli distribution are they're so different, right? One is completely discrete, yes or no. The other one's complete continuous function. And the fact that you can go, you know, you can work your way towards one of them from the other is truly amazing, in my opinion, right? Some people may not care, but like the whole idea, the way I think of it, is that all these distributions hang together and they're just different facets of different path statistics. And they're all kind of, you know, it's kind of amazing how they actually all kind of represent the same thing, it's just in different forms. I know that's not really the case, but that's the way I think of it. And it's like, it's so amazing like how statistics hangs together under these distributions, and how they all, you can get from one of them, you can get to all the others pretty much. Like I said, I don't know, I find that pretty interesting. Some people may not, but in this case, we have shown that the chi-square distribution, which comes from a normal distribution, is actually just a special case of the gamma distribution, which I think is quite terrific. Again, I'm not going to spend too much on that, but I think that's really interesting. So I hope you enjoyed this video. Again, I've got a blog post related to the chi-square distribution. which will be in the description below if you want to know, if you want a bit more material about it and all these proofs we just did. I've also got other channels. I've got my YouTube channel, GitHub, X, where I post more data science content if you're interested in that. I also write a weekly newsletter every Monday about my experience as a data scientist and giving you tips and tricks into the field and things you can learn. So with that, if you enjoyed this video, make sure you like, comment and subscribe, and I'll see you in the next one.